Welcome back, everybody. If you're new, my name is Nicholas, and this is Investing Against the Grain. So in today's episode, as promised, we're finally going to start covering a lot of the things that were discussed and uncovered within Tesla's AI Day a couple weeks ago. Now, this is going to be a long process, so we're going to split it up into multiple videos. Okay, so the goal is every Friday, unless there's some other big news going on with Tesla, I'm going to go ahead and release a video until we've completed all of the Tesla AI Day information and video and everything to go with it. Now, keep in mind, this was a very, very detailed and nuanced event for Tesla. It was very engineering centric, so I don't want to just breeze by everything, so that's the impetus behind making multiple videos. Okay, so with that said, we're just going to go ahead and get into it. But before we do that, do us a favor, hit the like button, hit the subscribe button, ring that bell. It really helps out the channel, helps it grow, and helps get this type of information out to more people. So if you could help us out by doing that, we'd really appreciate it. Okay, let's go ahead and dive into it.
What we want to show today is that Tesla is much more than an electric car company. That we have deep AI activity in hardware, on the inference level, on the training level, and basically, I think arguably the leaders in real-world AI as it applies to the real world.
So this is obviously Elon's opening speech, the keynote for the event, and I think it's very profound what he's saying here, which is very true, that Tesla is arguably the leader in real-world AI, okay? For implications moving forward, just from an investment thesis, this will be the next, forefront for just mankind, technology, everything. So being invested in a company that is, not just leading the way, but ahead of the pack by miles, right? It's a very profound and a very good thing to know and hear from the CEO, right? The CEO himself, and not just the CEO, but one of their main engineers in Elon Musk.
And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And so this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that later in the presentation.
Again, you can hear that Elon is referring to where they are currently with AI in that FSD, full self-driving. If you haven't seen any of those, just go to my Tesla playlist. I have a whole bunch of those. I make an analysis about each iteration that comes out. But what he's saying is that this is their first attempt at real-world AI. And the reason he's bringing this up is because they are very close to solving it, right? But obviously, he mentioned there are other applications and other things that they can do with this. So that's the whole point of this event, right? That's the genesis of it. So this whole event is about laying down the framework of what, one, they've done already, and then what they're going to be doing in the future.
So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on.
So just to give some context here, this is Andrej Karpathy, okay? He's the head of Tesla's AI, but really part of their vision team. So vision is what Elon was referring to, solving real-world AI problems, okay? Vision is one of the hardest things to figure out. It's not something you can just, manually code away. It's something that has to be done via neural nets. And Andrej Karpathy is arguably the world leader in neural nets. So much so that not only did he create the only course ever in Stanford for neural nets, but it has become one of the most popular classes or courses to take within Stanford. Okay. Also, just a note here, what Andre is going to go through is a few different examples of one where they were whenever he came on with the team, and where things are now and kind of the progression and evolution. He's going to try to break it down a little bit about what is actually happening within Tesla's FSD, within the Tesla neural nets, and translate that over to what we do as humans, right? How our eyes work, how our optics work, right? What it does, sending information from our eyes back into the neurons in our own brains. Okay, so let's take a look at this, and I'll chime in here and there wherever I think it makes sense.
Of the raw inputs that come into the stack, and then the neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car.
So when he refers to vector space, okay, there's two different ways to think about this. There's the images from the camera itself, right? So frame by frame, right? That's how camera works, each frame. But then there's also what we call vector space. So that's essentially taking physics into account, right? Taking time, taking velocity, taking acceleration into time, right? Rather than a still image, which is all a video really is a series of still images, right? Stitched together. But we're talking about in real time, right? If I'm driving the car and somebody's walking across the street, the vector space would be understanding that differential between me driving and whether or not they're going to cross and I have to stop, or if they're going to cross with plenty of time for me to just keep going as I am. Okay, so just a little information there about what he's referring to with vector space. Okay, it's about the implied actual movement of real world.
What I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the autopilot, and specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits light hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system.
So here you can see it reflects a lot of what I was just saying, where in a human's brain and the way we do things, right? We look at something, it hits our retina, it sends it to the back of our visual cortex, right? And then our neurons will go ahead and process the information. Same thing with the Tesla vehicles, okay? And again, he made a reference to we're essentially creating an animal, right? So he'll go into this a little more, but the vehicle is essentially the body. Okay, the neural nets are the brain. The electrical grid system is our own central nervous system, right? What's going on throughout our body. So there's a lot of synergies here as far as what, in order to create real world AI, right? So essentially simulating what an animal or a human would be doing and putting it into a machine or a robot and applying it to just robotics that would be real world beneficial.
At the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and have a lot of that scene context.
So that might have just sounded very confusing. But in other words, what he's really just saying is if you just put your finger right out in front of your face and you focus specifically on your finger, okay, it's really hard to see everything else that's going around you. So what he's saying is that there are neural nets, right, just like we have neurons, that will understand the perception of what's going on around us. So in other words, if we're not looking right at our finger, we can understand what's going on in the room, right? I'm aware of any lights I have, the table I have, my computer and all that, the camera right in front of me. But if I focus directly on my finger, all of that becomes a little blurrier, right? So what he's saying is that there are some neural nets that are taking an account of the bigger picture and some that are taking account directly close up, right? And just the subtle nuance of my finger, right? It becomes a lot harder to focus on everything else if I'm looking directly here. So what he's going to explain now is the relationship between both of those in order to make a very educated, predictive guess about what is actually going on in the surroundings based on that bigger picture, right? And that's how our head works, right? Our head works the same way. our head or brain.
For example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself.
So everything he just said there is a very complicated way of explaining my finger example. Okay, but understand it's very similar. It's the very same thing. The only real big difference between how our brains work and how this would work with FSD or Tesla AI would be that because it's camera based, it's a lot harder for the neural nets to learn. So for example, when we look at something, I'm looking straight ahead, I see my camera. Okay, I'm looking straight ahead, I see my beautiful fiance behind the camera. Okay, I know that instinctually right away. But with the neural nets, whenever they're looking at the images, the frame by frame of the camera, it's actually scrutinizing every single pixel that's in there, okay? Deciding the red, the blue, the green for each one of those pixels, and then it has to create an image in itself, right? So it's actually, substantially harder to create this than how our brains work, right? Now, obviously, there's a lot of intricacies within our own brains that we just don't understand, but this is what Tesla is having to solve, right? This is the level of detail and how hard this problem is, and it's why, up to this point, nobody has solved vision. Okay, it's not something you can code away, as I mentioned before. The only way to get to it is using neural nets.
Now, very quickly, we discovered that we don't just want to detect cars; we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly, we converged in this kind of a architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, hydronets, and these are the heads of the hydra.
So again, the hydronets, all he's talking about here is essentially, as humans, we actually suck at multitasking, okay? But when we're building this, we can make it so that this is very good at multitasking. Now, whenever we look at things, in a way we are multitasking, but what's happening is these hydronets, they're able to bucket different things. So I can create a bucket of just, is this a curb? Is this a lane line, right? Things of that nature. I can create another bucket just for, traffic symbols, right? Is that a stop sign? Is that a yield sign? I can make another one for, is that a pedestrian? Is that a animal? Is that just a random paper bag went by, right? I'm not saying this is how they have it broken up, but that's the idea, is that they can use these buckets, if you will, so that they can scrutinize and iterate on just those buckets rather than having to redo the whole stack all at once. Okay, I've actually talked about this. This was a theory I had on many of the FSD videos I've created, where I think that Tesla doesn't just send out the final of everything, but I think they actually send out different versions to each individual tester with different things that they've changed or biased. And when they get all the information back, that's when they iterate on their own. But this kind of confirms that, right? So this allows them to get more nuance with that, and instead of having something be so serial in operations and training, it allows them to really branch out and kind of get scale on their side.
This architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive.
And that just goes to, really solidify what I was saying and the theory I've had in my previous FSD videos, where they can go ahead, iterate on one task, on one subset of what they're working on without having to go ahead and do everything, right? This allows for, mass efficiency within Tesla and their AI team and their vision team.
So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these Hydra nets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the Hydra net. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you.
So again, what he's talking about here is just the difference between that image space versus vector space. So initially, FSD was using just image space. So again, I know you see videos here, but you have to understand a video is just a series of frames that are stitched together. Okay, it's not, a video isn't just a live stream like you would think it is. And so whenever the neural nets are trying to understand what's happening here, right, all they see is image by image. Okay, and what Andre's talking about here is that, you know, this had inherent issues with it, right? Especially for something like Smart Summon. If you don't know what Smart Summon is, it's this feature within Tesla where, you know, my car can be, you know, parked at the very back of the shopping, the grocery store. And let's say it's raining outside, right? And I don't want to get wet. Well, Smart Summon, I can just, on my phone, click Summon, and the Tesla will come to me, right? Instead of me having to run out there and get wet. Lots of implications for this, especially in the future, right? Imagine you get dropped off at the airport and your vehicle goes back home, right? So anyways, what he's saying here is that, you know, living in that image space, you know, it wasn't very good at predicting and planning. And so going into the vector space, right, this allows you to really understand the world, okay? It takes things from being essentially, it's still two-dimensional, but I would like to think of it as a very static kind of world when you look at it, especially going frame by frame, into more so of a predictive and thinking of it in a, you know, like I said, incorporating more physics into it, acceleration, velocity, where am I, what's going on around me, you know, is this going to move, is it not going to move, right? All of those things matter into this.
So we attempted to do this using C++ and developed what we call the occupancy tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with this setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end.
Again, this is something you can solve just by coding. You know, just as Andre said here, you know, they attempted this with C++, but it's not scalable, okay? You can't, it's not something that's very binary. It's not like I'm just, you know, coding a game to do X, Y, Z, where I live within a certain boundary of rules. The world has no rules, okay? Driving has rules to an extent, but something like being in the parking lot, there are no rules, okay? There are no lines where you have to stay on your side, right? People do all kinds of crazy things. So that's not scalable, and you know, it wasn't a real solution for what they were doing. It has to be trained within a neural net.
Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space, and the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these tiny, in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image.
Yeah, so you know, it's a great point too there. You know, any occlusion. So in other words, if part of something is obstructed and I can't see it, right, the image space really doesn't do you any good at that point. So again, just look real quick here. You'll see that on the bottom half of the screen, you can see what the prediction is, right? So this is the FSD AI making predictions. All right, Tesla doesn't use any HD maps or anything, right? The vehicle has to be able to see what's happening in the world and make inferences and predictions. So what you see on the bottom here, this is the best guess that FSD is making for the path forward. Again, this is within the image space. And the reason he talked about the top, as far as the image space, the lines look great, was because that's a still moment. Okay, but what happens, to his point, when you throw depth into it? What happens when there's an occlusion because something's covered halfway or 2/4 or just even partially, right? What happens then? This is where that vector space comes in and why it's so powerful.
So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve.
So what he's hinting at here is, and so if we have these 8 cameras, okay, and they're all feeding in, to the neural nets individually, okay, and in this example, I have a semi-truck going by me, okay, and I have, say, 3 cameras just to the right side of my car, right? Maybe I have one in the rear, one on the side, one in the front dash, and each camera has its own angle of that truck. Well, if what's being fed into the neural net is just the individual cameras, well, how does the neural net know that that's one continuous truck? It doesn't, right? There's no way for it to know. So what Andre's talking about here is essentially feeding into another neural net all of the videos together, stitching all of it together so there's a surrounding view so that the neural net that needs it can understand, oh, this is one continuous vehicle, okay? And then again, putting that onto the vector space rather than just from an image space perspective. And he gets a little technical here, but I don't think it's too hard to follow along.
But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are 2 problems with this. Problem number 1, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number 2, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling in images and so on is not going to get you there. You need vector space labels.
So we'll watch a little more with regards to this, but I kind of skipped over a lot of the technical on how they solve this problem. All you really know is, one, that they solve it, right? Or both of these problems, okay? So like he said, and he doesn't even really go into how they actually solve it. It's more so diagrams like this. So, even the technical aspect of it is more so just diagrams. But essentially what you need to know is that what he's saying is we have to go away from individual cameras in image space, and we need to take all those videos together. We need to combine them together, right? Fuse them together so it's as if there's one 360-degree camera. And then we need to go ahead and transpose that onto the vector space, and then we can apply it to one of the heads to actually do inferences. Okay, so all of this has to happen beforehand. So that's really what he's talking about here. Those are problems that they're solving, and that is the problem that they have solved.
So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images, and the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car.
So the important thing here to understand is, you see the top, and we can see how they're transposing these lines onto the videos that we see here. But what's really important to understand is below it, what you see in black, on the left was how things were done initially within image space. On the right is this fused videos in vector space. Now, the reason this is such a big deal is because, I think a lot of times people think, oh, we're just using the cameras of the Tesla, and so we know what the world looks like. But that's not how the neural nets work. The neural nets are actually taking that as inputs, and then they're making their own inferences on what the world looks like and what's real, what's not, okay? Imagine like having a child, okay? A child that knows nothing, all right? It doesn't matter if that child can look around and understand that, hey, yeah, I'm in the world, I can see everything, but that child has to learn that's a curve, that's a solid line, I can't cross that solid line. Oh, that's a double line, I'm allowed to do this. Oh, that person is walking, I can't hit them, red light, green light, right? You have to learn all these things, and that's what the neural net's doing. The neural net is learning just as a child would, just as a human would. And so what you see on the right, it's an example of the neural net's learning, and that's why you see on the bottom right these lines so much more solid, right? Because it's so confident in the predictions here, right? So that's what's happening. It's no different than a human learning. That's exactly what we're doing here, and as they go ahead and they improve and iterate on this, it's just going to get better.
This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions.
So again, just to highlight what Andre was talking about, the orange boxes you see here, these are just from single cameras, okay? You have 8 cameras around the vehicle, and so this is what each individual camera is showing and the prediction that the neural net is making. Now, if you notice, the blue, that is this stitched fused video that is placed in vector space, and you can tell that whenever he's going through these, and you can see the blue boxes are just a lot more solid, they're a lot more confident, they're less sporadic. Okay, that's one of the benefits of going to this new way of inputting the video information into the neural net.
Okay, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space, but we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture.
So again, just to kind of simplify what he's saying here, we're talking about memory, okay? When you're driving in a vehicle, okay, let's say that you are going to take a left and you are at a red light intersection. Well, when you're driving, you're going to see a lane marking that says only left, okay? And if you want to go left, that's no big deal. But if you want to go straight, it would be a big deal, right? You'd be in the wrong lane. Us intuitively, it's very easy for us, and we take for granted the fact that we can remember that we just saw that lane marking right behind us that's saying only left, okay? So we get to a light, we may wait there for a minute and a half. We don't even think about it. We know right where what that marking was. But with the neural net, right, we have to create some kind of cache. And if you're not familiar with the word cache, it's essentially just memory, right? So imagine you go to a website, and the first time it takes a little bit to log in, right? Or Netflix, okay? You go into Netflix, you go to log in, you have to put in your password and everything. You exit out of that web browser. The next time you go back on, it comes up immediately. That's cache, right? That's short-term memory for your computer, okay? So what has to happen here is the neural net has to create its own short-term memory or its own cache so that it can remember things it just saw. And it's not just lane markings, right? It's, okay, this semi-truck is taking a big left-hand turn, and now it's blocking that pedestrian I just saw walking across. Well, I need to remember that there was a pedestrian just walking across, right? Like, these are the things that are very important to getting to real FSD. Is having that short-term memory and understanding when I need it and when I don't need it, and when to draw on it. And then how long do I make sure the system keeps it into short-term memory, right? So all of this is what he's talking about here, and what we're trying to make sure that the FSD system has.
One by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled.
So again, when he says kinematics, just keep in mind, all we're talking about is velocity and acceleration, right? Just essentially a derivative of each other. So it's exactly what I've been saying, or derivative, yeah, well, an integral. But sorry, I'm getting a little calculus on you here. But so that's what he's talking about here, right? So keep in mind, he's going to say kinematics multiple more times. You hear kinematics, think velocity acceleration. Kinematics, velocity acceleration.
So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance.
So this is actually very clever on their part. Not only, when he says queue, he's just talking about essentially a line. Imagine like you're at a amusement park and you're waiting in line, okay? It's very, proper English. Instead of calling something a line, they call it a queue. So what he's talking about here is that there's only so much you can remember, right? Especially with short-term memory, right? If I told you to remember a series of random things like a dog, a deck of cards, a chair, a light, there's only so much you can memorize, right? So imagine all of those objects, that's your queue. And so that's what he's saying here too, right? There's a certain amount of things that we're going to have in the memory of the vehicle, in that short-term memory, and that queue, okay, or that line. However, what he's saying here is that we want that to only last a certain amount of time. And what he's talking about is, in milliseconds, obviously, but there's a certain amount of time that we want to be able to push this information to the neural nets to say, hey, this is the most recent memory, this is the most recent memory. But what he's arguing here as well is that that's not good enough just to have it be time-based. It also needs to be object-based. So in essence, if I've traveled the last, let's say, 2 blocks, maybe there's also an object-based queue of memory that sends that information. Because if it's just time delayed and I sit there at a stoplight for a minute and a half, I might clear out my memory and not have anything left. However, if I haven't traveled a certain amount of distance, well then I will still have that current memory that I have there until I actually travel a greater distance. So they're doing this in parallel. They have a time-based queue for memory, right? Or a time-based line of things that it can remember. And they're doing it based on object or distance traveled. Okay, so it's it's as if I'm taking a mental image of what's happening all around here, and until I travel a certain distance, I don't get another one, right? That kind of stays persistent for a little bit. So that's actually a very clever way to solve the issue they're referring to.
Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN, and these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road, like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space.
So besides the fact that this looks like something that you may want to look at if you're doing some mushrooms or something, the whole point of this is to just illustrate what the neural net is not only seeing, but what it's predicting and what it's keeping in its own memory. So what's really cool is that they're able to go ahead and let the neural net itself predict what to write, in other words, what to save in its own memory and what not to. So the neural net is now essentially taking over and making cognizant decisions on its own about what's important and what isn't. So if something is somewhat occluded, okay, maybe I don't decide to take this part of the occlusion and put that in memory. But the second that semi-truck moves away and I'm not occluded anymore, okay, well now I want to take that and put that into my memory, right? So it's become, this is where it's real world AI, right? It's definitely becoming the machine builds the machine trains the machine chooses what's important to the machine for it to learn.
Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly.
So before we actually watch this clip, which is actually pretty cool, understand that what he was just showing us was the vehicle making predictions as it goes. Have you ever played any game like Civ 6 or any kind of like Empire Earth or anything where you have to discover the world, right? As you go out, the map slowly starts to build out. Otherwise, it's just black. You can't see it until you get to it. That's what's happening here. As the vehicle drives, the neural nets are making predictions about which way the road's going to go. Is there going to be an intersection? What's happening? It's creating this HD map on its own as it sees. And what Andre, subtly refers to is that it's not building these persistent HD maps that you would see with a company like Waymo. Instead, the neural nets are creating its own HD map in real time with the real world and what it sees, right? In other words, just like the way we drive, right? We see and we make predictions. Oh, okay, well, I can tell there's a bend in the road, so I'm going to slow down, right? And I'm going to, take it, drive a certain way to take that turn because I'm predicting what's happening next. And that's what the neural nets are doing here. Now, before I hit play here, I want you to go ahead and take a note that if you look at the videos, especially the middle video, you'll see that there's two vehicles in blue boxes, okay, in the actual video in the middle. So keep an eye on there, because that's pretty much what Andre's going to be talking about moving forward.
So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent, and you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely.
Yeah. So, and again, just looking at these graphs, I mean, without, or these, this, almost sinusoidal wave, without knowing anything about it, you would just intuitively say that, the green and blue are a lot smoother than the orange. And again, the reason for that is because the orange is a single camera, whereas the blue is, again, the fused all 8 cameras into vector space, and then that's what's going into the head to go ahead and let the neural net make decisions.
So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing.
Okay, so that's pretty much the end of what I want to go over today. Again, you can see, they're already thinking about how they can even improve on this, even more so than what they've already done. It was really cool to see at the end here, everything just put together. And, I think it's a very small glimpse into what Tesla is doing, how they're solving this vision problem, okay? Obviously, even what we saw here was a very simplified version. They're obviously not going to share their intellectual property with all of us and talk about how they're solving these problems in depth. It's just going to be very surface level, box type diagrams. But what this should show you is that Tesla is a real world AI company. Okay, they're not taking the same approach as companies like Waymo, where they're just using maps that they're rendered around, and that can change 2 seconds later. They're not using, things like LiDAR, pointless sensors that don't allow you to truly understand what the world is around you. They're doing things the harder way, right? But the beauty of this is that once they solve it, they'll solve it for everything. Okay, and then the next step to this will be taking this and applying this to other things, other robotic type creations that Tesla can come out with. Now, again, I mentioned that I will be doing one of these videos, hopefully, coming up every Friday until we've completed everything. This was just 17 minutes into the about 2.5 hour long presentation. So I'm going to try to cover the more interesting things that were covered and try to give my interpretation of what's going on and try to, simplify things so that they're more digestible and provide more analogies and metaphors so that, it's just easier to digest. Okay, I mean, that's what I do as a career. I'm a software systems engineer. I design data centers, but I also help people understand how our software works by taking the complexity of things and translating it down to things that are more digestible. So, taking the complex and making it more simple. And hopefully that's what is coming across here with this video and this channel, and as I go through the rest of Tesla AI Day. Okay, so with that said, we're gonna go ahead and wrap it up. If you enjoy this type of content, if you want to help the channel out, if you want to allow more people in the world to get exposure to this type of content and understanding of what is really happening within Tesla with their AI team, there's a simple way you can help. And that's by hitting the like button, hitting the subscribe button, ring that bell so you're aware of any notifications. And with that said, I'll see you guys next time. Peace.